Hey everyone, welcome back, and today let's solve Leetcode problem 3350 titled Adjacent Increasing Subarrays Detection Part 2. So we covered Part 1 yesterday, and it's essentially the exact same problem, right? The exact same structure, and in fact the solution is pretty much the exact same. There really only is one different kind of pivot in this problem, and that is we have to return the maximum possible value of k, right? It's not what is it's not if it's valid or not. It's not just a boolean that we're outputting like yesterday's problem. We're actually returning the maximum or best case kind of scenario from our input, or in other words, the maximum possible k value that we can form between adjacent increasing subarrays that are strictly increasing, that is, in our input array nums. So I'm just going to quickly gloss over the problem statement once again, almost the exact same as yesterday's problem. Effectively, we just have to find the maximum integer k such that there exists two adjacent contiguous subarrays of length k, meaning they're one's right after the next one, meaning they're adjacent, and both of them have to be strictly increasing, right? So for example, we could have something like 7, 8, 9, and 2, 3, 4. And in that case, the answer would be 3 because that's the length of each subarray, and they're both strictly increasing, and they're both adjacent, right? And we're simply just returning the length of each of them, right? Which would be your maximum k value. And we have to try to maximize that value, which is the length of our adjacent subarrays. And not both of them combined, but rather just one of them, right? So, which leads us to the main observations that we really need to make in this problem, right? I'm not going to go over the examples. They're pretty self-explanatory here. I can link, and I'm going to link yesterday's video in the description for this video as well for you guys to check out. And the constraints are almost the exact same as well. It's just we have a little larger constraints, and so we want our solution to be efficient as well, right? But all of that's covered in the solution as well, similar to yesterday's video as well, right? So what is the only difference between today's video and yesterday's video, or today's problem and yesterday's problem? The solution structure itself is the exact same, but instead of actually returning if our maximum k value that we found was at least the given input k value, like yesterday's problem, we are just simply returning whatever k value we found, because that is the maximum possible k value that we could form as we're trying to maximize that as we actually iterate through our input array nums. So what is the main observation that we can really make in this problem? Again, very similar to yesterday. If a single increasing run is very long, meaning it has a length of per se L, that run alone can actually sometimes contain two adjacent increasing subarrays of equal length. And the two subarrays can be the first half and the second half inside of that long run. And so cur divided by 2, where cur is simply just the length of our current increasing run, could be a possible answer to our maximum k value. Or, and that's the first case, right? The other case is if we have two consecutive runs of length, previous and current, and the maximum adjacent k, using both of them would be bounded by the lengths of those two different kind of adjacent subarrays that are not connected, if you will, right? That would be computed by the minimum of the previous and current, right? Because the adjacency would require the first subarray to end where that second subarray begins. And again, a good example of that is example 1. 7, 8, 9, and 2, 3, 4 are both length 3. The minimum of 3 and 3 is simply just 3. That's our kind of bottleneck length, if you will. And to keep in mind, although these both are individually kind of increasing subarrays, 7, 8, 9, and 2, 3, 7, 8, 9, 2, 3, 4 as a whole isn't an increasing subarray, right? It's split into previous, which is 7, 8, 9, and current, which is 2, 3, 4. Previous would be set equal to 3 because that's the length of our previous strictly increasing subarray that we found last, and current would be also 3 because that's the length of 2, 3, 4, right? So those are our two different cases, if you will. And effectively, once we actually maximize those two values, as we find different runs and different valid adjacent strictly increasing subarrays, we're trying to maximize k and maximize that value, and we simply just return that maximized value after the single pass or single for loop after we iterate through the input array nums, and that would actually give us a constant extra memory because we're just keeping track of that singular integer variable as we iterate through the input, and that would be our maximized k value, which we'd maximize in the pass itself, right? So let's go ahead and get into the actual coding part of this solution. So again, I've said it a lot, but I'll say it again. It's very, very similar to yesterday's solution as well. We're initializing an answer. That is effectively what we return. That's our maximum k value, or our maximum valid k that we found as we iterate through the input. That's what we actually return. We're starting off at 0 because there is a chance that there may be 0 two adjacent increasing subarrays, right? There may be no two adjacent increasing subarrays. And so if that's the case, we'd simply return 0 for our answer. It'd never change, right? We'll also initialize previous. We talked about this in the example as well. The previous is simply just going to hold the length of the previous increasing run. That's basically just the run that ended right before the current run, right? And of course, we have to start at 0 because we haven't actually seen any runs yet, and the same logic applies to current. And the whole point of current is simply just the length of our current increasing run as we're actually counting that and increasing as we iterate through the input array nums. That's our current run, right? So now let's actually begin iterating over our input, and we're going to keep track of every index along with every element as well. So we're going to enumerate through the input array nums, right? So for every I and x in the enumerate of nums, I is our index and x is the corresponding value in the input array nums corresponding to that index, right? Because we want each index and value at each step, because we need the index to actually check the next element or detect the end to see if we're hitting the end of the input array nums or not. And for every iteration, we're going to increment our current by 1, because we're now including this element in our current length, or our current run. We have to basically, at each visited element, extend the current increasing run by 1, because this run is now going to include this current element. And we have to increment cur before actually checking whether the run ends at this index or not, because we have to account for this new variable, or this specific iteration, in our accounting as well. Now, the two different cases before we go into the other two cases is, have we actually hit the end of our input array nums, or do we no longer have a strictly increasing run? If either one of those conditions are true, we fall into our two cases of how we can actually maximize k, right? So if I is equal to the length of our input array nums minus 1, meaning we hit the last index or the end of the array, or x is now greater than or equal to nums at I plus 1. That means our current element is no longer strictly increasing in our current run. That means our current element is now greater than or equal to nums at I plus 1, the next element, rather than being less than I plus 1, because that's a property of a strictly increasing, right? When that happens, we must incorporate the current into our answer and then actually shift current into previous, if that's the case, if our element is no longer strictly increasing, or we hit the end of the array, right? We reach the last element, that is, right? And so we have to then update our answer using our kind of formulas that we discussed above, right? So answer would be the maximum of either itself, because we don't want to make it smaller, or the two different cases. The two different cases is current divided by 2, right? That's just the length of our current largest increasing subarray, and of course we have to split it into two equal halves, because those are the equal half lengths of our two kind of split adjacent subarrays that are both strictly increasing once this run ends, or the minimum of previous and current, right? Those are the actual lengths of our previous. Those are the lengths of our previous strictly increasing subarray that's adjacent, and the current length of the increasing subarray, right? Basically, that's just going to be whatever maximum value it is. And again, this leads back to that kind of main observation that we have to make, right? Any plateau or any break in the sequence where values stop increasing is basically just a natural boundary where we can actually try to form adjacent increasing subarrays using that just ended run in the previous run, right? That's why we always update answer at these specific boundaries in these iterations. And once we do that, once we actually maximize or update our answer, we then have to reset our previous and current length, because we're starting off in new runs now. So previous and current are not equal to current and 0, right? And then basically what we're doing here is we're initializing previous to be current, because our new previous value is the current run that just ended, because that's what we're going to use for future runs. And current has to be resetted to 0, because we're starting a new run for future elements, right? That's really the whole point of that. We have to just start fresh at the next iteration and reset these variables. And finally, once we completely finish this pass and have our answer to be maximized, or in other words, our k value to be maximized, we have to return our final answer. That's going to be the maximum k for which two adjacent strictly increasing subarrays of length k exist in the input array nums, which we maximize as we iterate through our input nums, right? So unless I made in syntax 0, 0, this should be accepted and this should be a valid solution. So let's go ahead and verify that. And as you can see, this really is just about as efficient as you can get it to be. So at a high level, how are we really solving this problem? Again, very similar to yesterday's. Effectively, we're basically just iterating through nums in a singular pass and identifying the maximum strictly increasing run and their corresponding lengths, right? And every time we actually kind of end a run, meaning we hit the end of the array, or we break our strictly increasing sequence property, meaning our current element is no longer strictly less than the next element, we have to consider two different cases for k, right? We can either split a long run in half, which is current divided by 2, or we can pair the previous run and the current run to be the minimum of previous and current, those two corresponding lengths of those runs. And we have to maintain the best or highest possible k values seen, which in other words is our answer, and effectively return that, right? Again, tying back to that main observation, very long strictly increasing stretches are very useful. Why? Because they can sometimes be broken into two adjacent strictly increasing subarrays, where our shorter runs can only contribute when paired with neighboring runs, right? That's why strong or very long increasing stretches are also very helpful, along with the second case as well, right? Which brings us to our complexities of the solution. So for the runtime complexity here, again, the same thing as yesterday's problem. It's going to be linear, or in other words, big O of n, and is simply the size of our input or the length of our input array nums. Why? Because this really is just a single pass solution. We're only using a singular for loop to iterate through our input, and so we're going to iterate through each element exactly once, and so that's why it's a big O of n, or linear runtime complexity. And our memory or space complexity is actually going to be big O of 1, or constant time,
And the reason why is because we're not actually using any extra memory or any extra data structures. We're only using a few integer variables like answer, previous, and current that don't actually scale in proportion with our input because they are actually integers. Right? We're not actually using any additional arrays or data structures. Right? So to kind of recap, the runtime complexity is linear, big O of n, and the memory or space complexity is constant, big O of 1. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I'll see you guys in the next video. Bye bye.